Hi everyone, thanks for this great opportunity to allow me to introduce this technology, LoTempLene, on behalf of our research team at Idaho National Laboratory, INL. My name is Dong Ding, a staff engineer and scientist at INL. I'm a principal investigator for this technology. Thanks to my colleague Andy to prepare these slides for me. So LoTempLene technology is a revolutionary electrochemical refining process that converts ethane from natural gas liquids into ethylene, the chemical building block used in making polymers from cell phone cases to disposable diapers by means of non-oxidative electrochemical deprotonation at intermediate temperatures, 400 to 600 degrees C, by co-production of ethylene and hydrogen. LoTempLene can achieve a reduction of process energy by at least 65% and carbon dioxide emissions by 17% compared to steam cracking, which was the industrial mature process for ethylene production. This transformational low thermal budget, low carbon footprint process could have pronounced impact on natural gas and natural gas liquids upgrading process for ethylene production. So here, customer for LoTempLene is petrochemical refinery companies who are looking for expanding ethylene production capabilities. In particular, those who wanted to engage clean energy or low carbon emissions with industrial electrifications. So a report has showed plastic production, which was 311 million tons in 2014, will double by 2034. Production of ethylene, the basic building block for these materials, represents the single most energy-consuming process in chemical industry. The abundance of shale gas resources in the United States has created a vast supply of low-cost methane and ethane that can be further processed into valuable chemicals, polymers, and liquid fuels. To produce these commodities, ethane is converted to ethylene, a high-value intermediate, through high-temperature thermal cracking process. However, steam cracking for the ethylene production is the single most energy-consuming process in the chemical industry. It's estimated to account for 60% of product cost. To achieve significant process in the reduction of both the process energy and the carbon footprint, single process optimization may not be sufficient because of the maturity of the manufacturing industry, either centralized or vertical integrated, where materials and energy efficiencies have been extensively optimized with a long track record of the reliable operation. So it's vital to develop disruptive methods that are both low thermal budget and low carbon footprint, aiming to fully exploit the potential of the ethane as a feedstock. So here's the solution. The figure on the left exhibits the working principle for the LoTempLene. It involves feedstock ethane is split into ethylene and protons in the anode by electricity. The protons migrate through the electrolyte, a dense ceramic proton-conducting membrane, to the cathode, where they combine together to electrons and form high-purity hydrogen gas. Look at the process energy figure on the left top. The beauty of the LoTempLene is to get two primary products separated by the electrochemical membrane, which allows the reaction to take place at the reduced temperature. Along with the small consumption of the electricity, the overall process energy is reduced by 65% over steam cracking. Furthermore, unlike the hydrogen being burned out as a waste in the case of the steam cracking due to the cost, LoTempLene provides the pure hydrogen. If we take hydrogen energy into account, we can actually get process energy gain. And then three scenarios are used to calculate the CO2 emission reduction. Even at the case we assume the electricity comes from the fossil energy, 72% carbon footprint reduction can be achieved, as shown in figure right down here. So here are more detailed comparison metrics between LoTempLene and steam cracking. Obviously, ethane steam cracking consumes typical 17 to 21 gigajoule of the process energy per ton of the ethylene, where it operates at 850 degrees C. It's estimated the steam cracking process contributes 60% of the product cost and 2/3 of the manufacturing carbon footprint. By iterating the low thermal budget and low carbon footprint feature for LoTempLene, we can further conclude the carbon dioxide emission can be reduced by 98% if we used both renewable-based electricity and excess heat. Moreover, electrochemical process can overcome the thermodynamic limitations by faster removal of the hydrogen from one side. This is another advantage for LoTempLene. So based on our electrochemical data, we conducted the TechnoEconomic Analysis. These figures shown here demonstrate the difference between LoTempLene and steam cracking for ethylene production from ethane in terms of the capital and operating cost. Left figure shows the total capital cost of LoTempLene. $345 million is about 1/3 of that steam cracker, $1.1 billion. On the right figure, for each ton of the ethylene produced, the operating cost of the LoTempLene is 7% lower than the steam cracking. So the takeaway is both capital and operating cost is reduced when LoTempLene is compared to the steam cracking, especially based on the assumption for the centralized plant. Given the fact LoTempLene is supposed for module-based distributed operation to couple with renewables, it may have more significant implications for economical feasibility. So here the research team for LoTempLene include Dr. Wei Wu, who is the research engineer responsible for the fabrication and testing of the electrochemical cells, Dr. Lu Chunwan, who is the scientist in charge of the electrocatalyst R&D and integration into the cells, as well as Dr. Ting He and me. This technology, LoTempLene, was initiated by INL Lab Directed Research and Development, LDRD, and received continuous support from DOE Energy Efficiency and Renewable Energy Office, Advanced Manufacturing Office. As shown figure here, enabled by developing new catalyst and integrating into the unique cells, we fabricated through our high-temperature roll-to-roll manufacturing technique, along with our home design testing fixture. We have successfully demonstrated the process feasibility in bottom cells, and the ethane conversion is about 41%, with the ethylene yield of 27% at 550 degrees C. The yield appeared to be increased with current density. The stability is much better than fixed bed reactions through a thermochemical process. So that means the electrochemical take effects during the process. So we are looking for the industry partners to support a competitive proposal development, as well as the manufacturing system up to 10 by 10 centimeter cells and further stack. So here are the contact information. Please feel free to reach out to Ryan Bills for any licensing questions. I'm the technical point of contact. Our emails should be below here. I guess that's all. Thank you for your attention. I'd like to take any questions.